to talk about equilibrium. There are two main sets of equilibrium problems. The first set is when an object is at constant velocity, or in this case, not moving at all. Alright, in this case, I have a mass hanging from two chords, and these two chords are at some interesting angle. The first thing you need to do in this type of equilibrium problem is to identify key points. In this case, there is a knot and a block. Draw a free body diagram of everything you have. Now, let me draw my mass here. This is my mass that's hanging, and I see if I cover up everything. Let me get a cover here. Alright, I'm going to use this to cover things up. If I cover this stuff right up here, I see the free body diagram for my hanging block. Tells me I've got FG going straight down, and this tension 1. I'm going to sum the forces, and this equals 0 because it's in equilibrium. It's not moving. The forces I have going up are T1. The forces I have going down are FG. So this must equal 0. So I know T1 has got to equal FG, and I remember that FG is equal to mg. So if I know my mass, I can find the tension T1. Tell you what, for simplicity's sake, why don't we go on and find the mass? Let's say M1 equals, let's say 3 kilograms. So the tension in the first block, in the first chord, is going to be 3 kilograms times 9.8. Alright, 3 times 9.8. I'll do this really quick. Is equal to 29.4 newtons. Now that I've done the mass, let me come down here and do the knot. And you do need to be very clear and label these. I'm actually going to do them in different colors. Now do a free body diagram of the knot. Well, let's see. The knot has no mass, but I've got T2 coming up at this angle. I have T3. Now T3 is horizontal in this case. It doesn't have to be. There can be another angle. And then T1 is going straight down. The first thing you need to do is resolve all of these into components. So this is theta. That's not very good theta. Try again. Theta. We'll put a number in here in a minute. And I'm going to take T1, and I'm going to go on and sketch out T1x and T1y in yellow. Now I know T1x is the value of T1 times the cosine of that angle, and I know T1y is T1 sine of this angle. I guess this is T2, isn't it? So I should change these to 2's. Sorry about that. I've already found T1. Now, T3 is at 90 degrees. We're going to leave that alone for the moment. If T3 were at an angle, I would need to find T3x and T3y. As you can see, I'm setting up my x, y columns. The beauty of this is we can always treat these completely separately. Now let me get another box. The first thing I'm going to do is ignore or cover up. Oh goodness, I've got too many going here. We're going to ignore everything covered by those blocks. Matter of fact, let me even bring this to the front. Oh, it doesn't want to. Alright. Now, what do I have acting in y. Let me do y first. I have ty and T1. Those are the only forces acting in a vertical manner. So, I have the summation of the forces in y is 0. I have T2y acting up, and that's minus T1. And you know what? This is T2y and T2x. Apologize for that. And this equals 0. So T2y has got to equal T1. And T2y, you remember, is T2 sine theta. So this is T2 sine theta equals T1. Now suppose I tell you that theta is, I don't know, 30 degrees. Nice number. As soon as I do that, I can find T2. T2 then is T1 divided by the sine of theta. So it's 29.4 newtons divided by the sine of 30. And that gives me 58.8. So T2 is sitting at 58.8 newtons. Now I go back to my X column, and I'm going to ignore everything happening in Y. The only forces I have acting in X are T2X to the right minus T3, and this has to equal 0. So if I solve this for T3, T3 is T2x, but I know T2x is T2 cosine theta. Well, I just found T2 is 58.8, and I'm going to multiply that by the cosine of 30. So I get T3 is 50.92 newtons. So this type of equilibrium problem is actually fairly straightforward. You just sum your forces and set them all equal to 0. In this kind of equilibrium problem, well, it gets a little bit more complicated. I have this ladder, and let's assume this is the center of mass of the ladder. You remember the entire body will act as if all of its weight is located at this point right here. So, this force acting straight down on my ladder is Fg. Now the ladder is resting on the ground. So, because it's resting on the ground, there will be an F normal 1. It is tending to want to slip this direction, and we know friction opposes motion, so we're going to have some friction acting back to the right. Because it's leaning against the wall, there is another normal force. This is Fn2. And of course, if there were friction acting on this wall, because it's wanting to rotate down, that friction Fr2 would act straight up. Now, in order to be in equilibrium in a situation where you're attempting to rotate, you need 3 conditions to be satisfied. The sum of the forces in X must equal 0. The sum of the forces in Y must equal 0. And then the sum of the torques must equal 0 as well. And this is the sum of the torques about any and every point. Oh my goodness gracious. Let's see what the sum of the forces in X looks like for this. Sum of the forces in X equals 0. So let's see. What do I have acting to the right? The only thing I have acting to the right is the force of friction 1. And to the left, I have Fn2. So what this tells me is my frictional force from the floor must equal the normal force of the wall. So, pretty much, if there is no friction, there is no normal force. So, if this were a perfectly smooth floor, this ladder would not stand. Next, let's sum the forces in y. And this has to equal 0 as well. Let's see, what do I have? I have Fn1 plus friction 2. This is a friction along the wall. And then minus the weight of the ladder. So I'm just going to put minus mg. So this equals 0. So if I'm looking for this normal force on the ground, I see it is going to be the weight of the ladder minus the frictional force on the wall. The third condition you have to have is the sum of the torques about any point equaling 0. So pick a point. Pick any point you want, but I always like to pick one that's got things I want to get rid of. So let's sum the torques about this point here. I know that any force that runs through there will have a lever arm of 0. Oh, we need to find our lever arms. Let's see. What if we call this distance here x, this horizontal distance, this distance here y, and if the ladder has a length L, in general, in this case that's not the case, but in general, the mass isn't going to be in the center. The center of gravity is going to be in the center of the ladder. This ladder is off. So let's just call this L over 2 because we can. Not drawing a scale. How about that? So let's look at the sum of the torques. About A. The first thing you need to do is determine the lever arm of each force. Alright. Let's look at about A, Fn1 and friction 1 have 0 lever arm. So these are not going to contribute to the torque. But what about Fg? Fg has a lever arm of, let's see, I'm only concerned about the force acting at a perpendicular distance. So I'm looking at this distance right here. We need to do a little trick. If this is the angle, theta, and you can find that using x and y, then Fg will have a lever arm of L over 2 times the cosine of theta. Is that right? I want the x component. The length of it is L over 2. Yep. The lever arm for Fn. Now, how far away is Fn from this point? If I extend this line, it's easy for me to see that the lever arm for Fn2 is going to be my y distance, while the lever arm for the second friction is going to be, I'll bring this down, it's going to be this x distance. Alright, put your finger right here. Gravity is going to want to make this go in a clockwise circle. So this is going to have a negative torque. So this is going to be minus mg times, let's see, L over 2 cosine of theta. Fn2 is going to tend to want to make this go counterclockwise. So this is going to be plus Fn2 times the lever arm of Fn2, which is just this big line. And then this frictional force is also going to want to cause a counterclockwise motion. So it's going to be plus the frictional force times its lever arm, which is x. And this has to equal 0. So we're just going to have to algebraically solve this somehow. We could do the exact same thing about this point right here. or about the origin, or about some point up here in the corner. When you do problems like this, you need to remember, say someone is placing books on the edge of a table. Suppose I take a book and I put it at P1 and it has some mass. Then if I would like the torque of this, if I want this to be in equilibrium, then I will have a normal force here and a normal force here. Left and right. I could have called this left and right. I'm going to have the mass of the tabletop going down. I'm going to make that T. And then I'm going to have the mass of the block going down as well. So I need the sum of the forces in Y to be 0. So I have F in 1 plus F in 2 minus M G minus mass of the table G. So it looks like the two normal forces, F in 1 plus F in 2, have to equal gravity times the sum of the masses. That kind of makes sense. But that's not enough to give us our answer. So let's sum the torques. In general, you're going to want to sum your torques about a point. Usually you're wanting to find the normal forces on these problems. Let's sum the torques about P4 because we can. You basically need numbers here or something. Let's see. Let's let the distance from P1 to P2 to be D1. This is D2, and this is D3. So if I sum the torques about P4, what are we going to have? Well, F1 in 1 is going to tend to make this rotate in a clockwise manner. So it's going to be minus F in 1 times the distance. Let me just call that D3. The weight is going to tend to make it rotate in a counterclockwise, so that's going to be positive. So it's going to be plus the mass of the table times G times D2. The first normal force is also going to want to go in a clockwise manner, so it's going to be minus F in 1, times D1. And then the third mass sitting on the end, let's call that D sub 0 since we're going that way. This is going to tend to rotate in a counterclockwise manner, so this is going to be plus M, G, that's little m, times D sub naught, and all this equals 0. In the problems, you will have enough information to sum your torques and get a solution. A more practical problem involves a bar with a hinge. What you're always going to want to do is sum any torques about the hinge. The wire is going to be going off at an angle, theta. And let's say this has a length L. When you do the free body diagram, alright, you have FG going down, and then you have the tension going up at an angle. Now, I'm going to draw this right here, even though I don't like doing that for free body diagrams. There has to be a force, tension's pulling up, so there has to be an X force to counterbalance this X part of the tension. Now, let's sum the forces in Y. Summation of the forces in Y equals 0. So I will have Ty minus Fg equal to 0. So the tension in y, so T sine of theta, has to equal mg in this example. Let me sum the forces in x. This equals 0. So I have whatever this applied Fn is, or sometimes we call it a hinge force. Let's just call it Fn, minus T cosine theta equals 0. So the hinge force has got to equal T cosine theta. But this isn't usually going to be enough information for us, so we need to sum the torques. Now you can sum the torques about any point you wish. I strongly recommend you do it through, I don't know, the hinge. All right. Oh, no. Let's sum it about this point right over here. That way we don't have to worry about T and its angles. Actually, we still do. All right. The sum of the torques. What you need to do at this point in time is break T into Tx